About a year ago, I thought to myself, Osu's an easy game. I'm bad at it, but I'm sure a computer wouldn't be. And so, I started on this journey where I tried to beat Osu in every way possible. Now, what sparked this event was interesting to say the least. Here's a dramatic reenactment of exactly what happened.
Oh, brother, this guy stinks!
Step 1, data collection. So, our data needs to be two parts. We need some images to feed the AI, and then we need corresponding cursor positions so it can learn this image, and by therefore this situation is this cursor position, and that teaches it how to move. However, this image, it's too good. It's too complicated, there's too much detail, and although it's already grayscale, originally would have been color. So all these things are bad, so what we're going to do, we're going to make images grayscale, we're going to make them lower resolution, and then we're going to blur it. And all of these just act to make that image more simple and more amenable to AI training. Let's talk about grayscale. So it's key to remember in most applications, they are stored as effectively three sub-images, a red, a green, and a blue, and this gets translated into red, green, and blue LEDs being on in your monitor or screen, and then that tricks your eyes into thinking that that color is showing up, and the amount of red, the amount of green, round, blue is essentially the brightness of the LED. All of this is a lot of data, and we don't need it because it's OSU. Simple game, easy game, no need for all of that stuff. Instead, let's have a couple grayscale images, and these represent everything that we need because again, in OSU we can derive the order based on the outer collapsing circle that you can see there, and so that means that we don't really need color at all. So color is just useless. Rather, let's use that capability to feed it essentially a small video instead, a really, really short video with context, and that gives it a lot more predicting power that just having some things in color just doesn't do that much. So first, make images grayscale. Let's talk about image resolution. So image resolution just gives too much detail, and there are some small details that the AI might grasp onto and then learn from that specifically, which is really bad. We don't want that. This is because the image is represented as a huge number grid, and when the AI processes that, it's effectively doing operations on that number grid, and that's a lot of stuff to contend with. We want to reduce that so the operations go faster, and that has its own use on its own. So instead, what we're going to do, we're going to make them blurrier, and you know the blurrier the image has just physically less data in it, and then that really just makes all the operations faster, no details, stuff for it to grasp onto. Just generally is going to be a much better training experience. Let's talk about blurring. So, unlike image resolution, blurring kind of smears the data around. And that means that those details that originally would have been there for stuff to grasp onto just instead get smeared all over. And that means that it focuses on the big stuff, on the big main things to focus for us. That's the circles. So the AI no longer has the ability to grasp onto small details because they all got smeared around and can't be accurately represented. When this is used in conjunction with low resolution, super powerful. So our three steps are making images grayscale, low resolution, and blurrier. Let's talk about the actual cursor inputs. So this, it's really important that they look like a human because this is going to decide how the AI actually, in every single situation, it's going to use these inputs to infer what is going to happen. So for us, we're going to use Rex inputs, and that's because he's the best human, and also he has replay files, which effectively give us all of his positions at every second. So we're going to use the fact that all of his ranked play have replay files, as Osu always does, and then we're going to rip those out, and then we're going to convert them into positions, and then we're going to match them up with the actual video, the actual replay itself, and then we can essentially use that information to match up all the processed images with processed inputs. And now we have a list of images to inputs, which is the data that we want. Now we can design model architecture around what data we have, and then we can also figure out how we want to predict everything. But now we're done with data. So part 2 of my project now is model design. So there's a lot of model architecture that I can use here. I can even combine a bunch of common architectures into one big model. But for this, I'm just going to be using a simple convolutional neural network. And this is because it's really good at processing images. It's really good and really simple and also produces great results. And finally, because of my experience with it, it's really easy to maintain for me and easy to fix. So what exactly is a convolutional neural network? Well, a convolutional neural network essentially takes these small chunks of the images, pass them through quote-unquote filters called convolutions, and then from there pass them through a neural network which kind of just thinks about all those image data. So convolutions specifically are kind of these learned filters, as you can see here. This one specifically emphasizes the edges. It can emphasize any number of things that the AI learns is important, so it can basically process the image in any way they want. So now, with that in mind, what exactly is a neuron? So a neuron works exactly like human neurons. Well, not exactly, but close enough. And they essentially take in inputs, and then based on what they've learned, they weight these inputs, which is essentially just multiplying them by some value. Then they sum all of those numbers up, and then they pass them through a nonlinear function. Typically, this is something like sigmoid or hyperbolic tangent or ReLU, which is really just a straight line. And all of these allow the neuron to represent nonlinear relationships. So then it creates an output based on that. Neural networks essentially just chain them together so that the output of one neuron can get fed into another neuron. And what this essentially allows each neuron to do is specialize maybe on focusing on different things, or just chain and get more modeling power because there's simply more components in play. So specifically for a traditional neural network, they usually have some kind of input layer which get passed into some hidden layers, and these hidden layers do kind of most of the thinking. Input mostly does like the processing, and then they have output layers which take all the hidden layers and then make an output. So then, now that the whole model is basically all designed and written, the only thing left to do is just train it and see how it goes. So now with that all done and dusted, I guess, and here is the results, and I'm gonna let it play in the background. And so as you can see, it's pretty good. It's really good actually. It's a little too good. Now that it's actually pretty good, there's really no reason to train it, but I did have to kind of baby that for a week and tune a bunch of values over and over again. That was really annoying, and I don't want to do that again. So instead, we'll be using another method called reinforcement learning. So even though I got good results, I could get better ones faster with reinforcement learning. So the difference between normal learning and reinforcement learning is that normal AI deep learning basically calculates how wrong it is. Like, you have a key and you have produced outputs and you calculate how wrong it is, and use it to directly affect the actions being taken. Use that to directly affect the neurons. What happens in reinforcement learning is that there are actually there are sometimes two networks depending on what type you're using. For this, we're going to be using proximal policy optimization. And for that one specifically, we have two networks. We have an actor and a critic network. And the actor does something, then the critic criticizes that actor's moves, and then from the criticism, we figure out which action is the best, and then we use that as our output. And then we use that to go affect the actor and the critic networks later. And what this effectively does is the AI does learn what it's doing, but it also learns that out of what it's doing, what is the best move. It effectively can figure out what actions are good or bad. And that's really important because then if we put it into a completely different scenario, it can figure out what to do really quickly or just be really good at that scenario because rather than figuring out directly what to do, it figures out what to do and what good things have in common, so to speak. So it basically just it learns a lot more about what actions there are to take. And that's really important. And that means that the AI can adjust itself a lot better than with deep learning, for example. Overall, just a much better system, and it also applies a lot more to OSU. So for this, basically all that's left to do is for me to just sit back and play some video games.
Remember the Placidium! Zelos! Kai! Rue! Yeah! Ha! That's not my...
So as you can see, it ended up being also really good. So whether we learn reinforcement learning is amazing, and it's way better than everything else I did. And deep learning is dead unless I want to have a life at some point. The only really annoying thing about reinforcement learning was that was just a lot of setup. Like honestly, all the work that I spent tuning was just converted into setup. So it was kind of really annoying to do that. But other than that, genuinely pretty simple. So yeah, project done. And next, I think I'll make an AI streamer out of this.